I made a video a while back about how plate tectonics hasn't always involved plates on Earth. There were tectonic regimes on Earth that didn't involve plates very, very early on, multiple billions of years ago. But recently, there was a paper published suggesting that we should reinterpret the evolution of tectonics on Earth. This new 2024 paper by Robert Stern has been published in the journal GSA Bulletin, and it challenges our understanding of how long plate tectonics has been operating on Earth. Now, when you hear the word tectonics, especially with regards to Earth, you probably imagine Earth's crust broken up into a bunch of plates that are shifting and colliding against each other and spreading and all these things that we talk about, which is modern plate tectonics. This is how tectonics works on Earth today. And plate tectonics has shaped Earth's mountains, ocean basins, and even in large part, climate and conditions for life. But tectonics on Earth hasn't always involved plates. Like I mentioned earlier, I have a video that I posted not too long ago that was actually an interview with Stephen Bauman, a early Earth tectonic scientist. We talked about essentially how tectonics hasn't always involved plates in that video. And we talked about the evolution of plate tectonics and when it's thought that plate tectonics finally became the global regime on Earth as it is today. And we talked about these major stages of tectonic regimes throughout Earth's history in that video, starting with one, the magma ocean stage, so essentially very hot molten Earth when it just formed and it's still solidifying, and so it's just a magma ocean, which is crazy cool, but that was 4.5 billion years ago when it had just formed. And then heat pipe Earth, still very, very hot Earth. The crust is starting to solidify, but it's still very volcanically active and hot. And the mantle is still very hot and driving a lot of activity at the surface. And the lithosphere and crust haven't really begun to become distinguished in the way that they are today. I should mention that the lithosphere and the crust are two different things. Crust is the thinnest, most outermost layer of Earth's material, and it's very silicate rich, which is less dense than the layers below it, like the mantle and the core. But the lithosphere includes both the uppermost mantle and the crust. Why do we designate a word for the lithosphere? Why don't we just go with crust, mantle, core? It's because the lithosphere is actually what makes up the plates. It's not just crust moving around on Earth's surface that causes plate tectonics. It's actually crust as well as the uppermost part of the mantle that moves around and makes up Earth's tectonic plates. So why do we designate crust as being different than the lithosphere? Why don't we just call the lithosphere the crust? Because of density differences and compositional differences that I won't get into here. But the gist is, crust is the thinnest, most outermost layer, and the lithosphere includes both the uppermost part of the mantle and the crust. And then the lithospheric plates, the tectonic plates, ride along the asthenosphere, which is more of a plastic part of the mantle that kind of convects and allows these tectonic plates to move around on Earth's surface. That said, at this point, 4 billion years ago, as we go through Earth time, these lithospheric plates have not developed yet. Then we get to a tectonic regime on Earth around 4 to 2.5 billion years ago in the Archean eon, which some people call drip tectonics. Essentially, the lithosphere has started to develop. That's the green part here. The purple is the crust. And the lithosphere is undergoing deformation and tectonics, where heat is being released at the surface and deforming the surface, and stuff is going back into the mantle and recycling, similar to how plate tectonics does today, but not the same. Essentially, the best way that I've had this explained to me by Steve in that previous interview video, is that plate tectonics is more lateral and drip tectonics was likely more vertical. So today we have these rigid lithospheric plates moving across our surface, subducting and spreading from mid-ocean ridges in a very lateral way. It's laterally continuous with these rigid lithospheric plates, whereas on early Earth, pre-plate tectonic Earth in the Archean, 4 billion to 2.5 billion years ago, drip tectonics was driving tectonic activity, where essentially the thing analogous to subduction on Earth today was this dripping, which was much more vertical than subduction today. And then we had upwelling and plumes, like hotspot type volcanism during this time as well, but it wasn't necessarily, subduction driven volcanism that we see in a laterally continuous regional way today. And then finally, starting around 2.5 billion years ago, is thought to have been kind of the beginning of this transition to global plate tectonics. Well, I shouldn't say beginning of the transition. It's thought that by 2.5 billion years ago, so anywhere from 3.2-ish to 2.5 billion years ago, there was this transition from drip to plate tectonics, and then around 2.5 billion years ago, there was enough plate tectonics going on Earth at that point that most geoscientists seem pretty comfortable to call that globally plate tectonics, or a global plate tectonic regime, which has continued until today. And then in the far future, we will eventually have what's called stagnant lid tectonics, where as Earth, so throughout these regimes that we've gone over, these past, 4 regimes we've gone over of tectonics in Earth's history, these tectonic regime transitions have been caused by Earth cooling over time. It was really, really hot at the beginning. It had magma ocean, heat pipe tectonics, and then finally crust started to cool, lithosphere started to cool, and it was drippy and really hot still, and then it became more rigid and platey. So as Earth has cooled, it's led up to plate tectonics, which will eventually lead into stagnant lid tectonics, where essentially Earth is tectonically dead at the surface. There's not enough heat from the interior driving surface tectonic activity or surface heat release. And then Earth will continue to cool until, the sun explodes 5 billion years from now, or whenever that's supposed to happen. But, and this is what we'll talk about in this video, the new paper by Dr. Stern in 2024 provides a new perspective on this story. I should mention also that this figure showing these tectonic transitions is also from a Stern paper. He has led a lot of this research into the tectonic history of Earth, and so I believe this one's from originally Stern et al. 2020, which I'll link below. He also has a 2023 update, and then this new 2024 paper, which kind of provides a new perspective, a very incredibly interesting new perspective on the last 2.5 billion years. So we're still keeping with the assumption that this, this transitional history from 4.5 to 2.5 billion years is around the same as what we have talked about here. Obviously, there's still a lot of research going into this, but this is kind of the main hypothesis that we're going with right now. And then he then provides a little bit new perspective and evidence behind some new ideas regarding the last 2.5 billion years of tectonic history, so a little bit more recent. Essentially, instead of just, plate tectonics began 2.5 billion years ago and has been the thing that Earth has been going through the last 2.5 billion years to today, Stern suggests that Earth has alternated between plate and lid tectonics over the past 2.5 billion years. Now, when I say lid tectonics, I don't mean stagnant lid, like tectonically dead or inactive bodies like the moon or Mercury. I mean active lid tectonics, like what happens on Mars or Venus, which are both lid tectonics, but different types of lid tectonics. Sluggish lid is kind of what he describes as slightly slower or less active mantle convection, slightly less activity, and then the Venus scenario, the squishy lid scenario, is more activity, but again, lid tectonics, meaning one singular crustal, shell of a planet or moon, body, rather than a crust or shell broken up into plates. So essentially the difference between these two, he describes it as, picture an eggshell. Now, if you have an egg that has a shattered shell and there's different fragments or plates at the surface, that's kind of, where we get plate tectonics, the idea of plate tectonics, which is simple for us to imagine, right? Because we have grown up with this idea, at least, my generation has, maybe not people older than me, which we didn't know what was going on. But we now know this is what goes on modern Earth, this shattered eggshell picture. But single lid tectonics is this unbroken eggshell that still allows for deformation and volcanism, but with no plates. So he kind of shows a little diagram of this here. It's similar to the drip tectonic regime, kind of this vertically driven tectonic activity that doesn't involve rigid lithospheric plates. Now, this might seem odd or unusual or kind of hard to imagine, but it's actually more common than you might think. Actually, plate tectonics is the weird child of the planetary family, at least in our solar system. So what's interesting and what I love about this, so I should mention most of these images that I'm showing here are figures, or at least parts of figures from his paper. So I will link that below and you guys can check it out. But essentially, I love this figure because he showcases examples of each type of tectonic regime that, we go through as we go through Earth's evolution of tectonics. Early on Earth, we probably had a magma ocean similar to the asteroid Vesta. Then Io's tectonic regime is likely similar to this heat pipe scenario on early Hadean Earth 4 billion years ago when it was still very, very hot, just beginning to solidify at the surface. And then Venus's tectonic scenario is this kind of lid tectonic scenario where, it's just like what we just talked about. It's one single eggshell, unbroken, but still able to deform and have activity at the surface, upwelling and volcanism and downwelling. Oh, that's more of an oceanic term. But anyway, down dripping of crustal and lithospheric material down into the mantle for recycling, just in a more vertical way than plate tectonics. And then I love that he puts this stage of plate tectonics here as optional, because this is Earth. This is where Earth is currently at in its stage of tectonic regime as it cools. And it is kind of optional if we look at all the other planets and moons that are similar in composition, that is mainly silicates, so silicate minerals, which, Earth is a rocky silicate planet, as are these other planets and moons. If we look at bodies like that, we tend not to find plate tectonics. We find lid tectonics like on Venus or Mars, or, dead lid tectonics like on the moon. Or Io, we have this pre-lid tectonic scenario, but it will probably also go into lid tectonics. It's very rare that we find that planets go into the plate tectonic regime. I mean, I say very rare. We don't know of any other than Earth. So, at least not to my knowledge. Comment down below if we have found any maybe exoplanets that, I don't know, I don't even think that we could detect that for an exoplanet. But Earth is a very unique scenario, is what I'm trying to point out. And I actually have a video on my channel where I talk about whether plate tectonics is required for life or vice versa, which is an interesting concept because we talk about this possible link between plate tectonics and life that has been proposed for Earth. And one of the major things that links them together is the necessity for water. It turns out that there's a lot of people that think that water is one of the major things that drives plate tectonic motion and the physical capability of the lithosphere to break into plates and subduct and do all the plate tectonic things that it does on Earth is this liquid water at the surface. And this is really interesting because, again, liquid water being stable at the surface of any planetary body is a unique thing that we don't see very often. And so Earth is, again, very unique for this. So it could be that the stability of liquid water at Earth's surface and its kind of perfect Goldilocks scenario that it's in maybe gives it this unique ability to do the optional plate tectonic stage before it goes to a slower lid tectonic regime and then to a stagnant lid tectonic regime. So anyway, Dr. Stern is proposing that Earth has alternated between lid and plate tectonics throughout the past 2.5 billion years. But before we get into the exact timing of the transitions that he's proposed in this paper, you might wonder, how exactly do we study ancient tectonic regimes? What's the evidence that we can use to support different tectonic regimes in Earth's past compared to today? Well, the rock record preserves what we call tectonic fingerprints that trace tectonic regimes and episodes and transitions throughout Earth's history. Just to name a few, there are certain types of rocks like ophiolite sequences, ultra-high pressure metamorphic rocks, or blue schists that indicate plate tectonics. These are rocks that, or sequences of rocks that we know can only form, at least under our current understanding, can only form due to plate tectonic driven processes. And then there are also rocks that we think form under lid tectonic scenarios, or processes we think are associated with lid tectonics. And, we, of course, have ancient Earth to tell us about lid tectonics, but also modern other planets that are currently in lid tectonics. So, ancient Earth isn't our only lid tectonic example. We have Mars, we have Venus, and we do a lot of studying of their geologic features and tectonic features at their surface to understand what ancient Earth might have looked like, and what relics from ancient Earth, from the rock record, tell us about Earth's tectonic history. So using what are called plate tectonic indicators in rocks and single lid tectonic indicators in rocks, Dr. Stern was able to kind of put a timeline together of these transitions. And I should mention, these fancy chemical data graphs that I'm showing at the bottom here aren't, I'm not going to go through this all. You don't have to understand this all. I'm just putting it up on the screen because these are some examples of figures Dr. Stern used in his paper, and from other previous references as well. He kind of pulled together a bunch of past literature as well as his findings to paint this picture. And these are some examples of some of the figures he had showing the geochemistry of the rock record through time and what that indicates in terms of tectonic transitions. So feel free, it's going to be, again, linked down below. Feel free to dive into these figures further if you're interested. So getting to the timeline now, he identifies 4 episodes of tectonic transition from lid to plate and vice versa over the last 2.5 billion years, starting with a single lid tectonic episode from around 2.4 to 2.2 billion years ago, moving to plate tectonics from around 2.1 to 1.8 billion years ago. Then in the boring billion, what we named the boring billion, which goes from around 1.8 to 0.8 billion years ago, the boring billion, we nicknamed it because it seemed like a pretty tectonically stable, biologically stable, chemically stable, climatically stable period in Earth's history. That said, I do have a video about it that kind of goes over caveats with regards to that nickname and what we've found since nicknaming it that might hint at it being not so boring after all. So please check out that video. I'll link it to the top right if you're interested. But anyway, during this boring billion period, we switched back from plate tectonics to lid tectonics, and then finally we switched around 800 million years ago, or 0.8 billion years ago, back to our current plate tectonic regime, which has lasted since then. Note, though, when we talk about these transitions, that there is probably 0.1 to 0.2 billion years between each one of these. That's 100 to 200 million years of time between these transitions. So it's not like it was a flip of a switch. These transitions took millions, hundreds of millions of years to transition, if that makes sense. It's not like plate tectonics can go to lid tectonics and vice versa very quickly. Again, tectonics is a very slow thing, but it's possible that these transitions could have occurred over very long timescales. Okay, so we have this new paper that says maybe plate tectonics hasn't been the global regime for the last 2.5 billion years. Maybe there's been these transitions between plate and lid tectonics. But why does this matter? Why do we care about this? Well, understanding Earth's tectonic history helps us decode our mantle processes today and what kind of activity might it drive at Earth's surface today and in the future. But it also helps us understand why our mantle is hotter than models predict. Plate tectonics is very efficient at cooling Earth's mantle because it brings down this cold, dense oceanic crust and lithosphere from Earth's surface down into the mantle. And again, as we talked about in the timeline, Earth has been cooling over time, and the more that we cool its interior, the closer we get to that stagnant lid, tectonically dead body scenario. But Earth's mantle is hotter than models would predict based on our understanding of tectonic evolution through time currently. So maybe these episodes of single lid tectonics throughout the last 2.5 billion years slowed the cooling of the mantle enough to cause its current hotter than it should be state. That said, there are many, many, many ideas about tectonic evolution throughout Earth's histories. This is just one hypothesis, so it's not, necessarily the only idea or way that we can get around this or explain this. So, that's an idea. But another reason why we care about this, and particularly my favorite reason, is that tectonics is closely tied to life. As I talked about, I have a video on my channel where I talk about the tie between, or one of the major ties between plate tectonics and life, where I focus in that video on water, but there are many other reasons that plate tectonics is super important for life on Earth. For example, it supports biodiversity by creating diverse habitats and cycling nutrients. The cyclic nature of plate tectonics cycles nutrients through Earth's interior and transforms them back, kind of recycles them back into stuff that life at the surface of Earth can utilize, which is really, really important. It's actually one of the major things we look at for other planets, whether they're tectonically active, to decide whether they may be habitable, because tectonically active bodies mean that that body has some sort of nutrient cycling scenario, and that can feed life. It can literally feed life, which is so cool. And it's thought that plate tectonics specifically on Earth may have played a role in the evolution of complex life. And it's possible that plate tectonics, given its rarity, could help explain why intelligent life seems so elusive in our universe. That said, I don't want to make it sound like plate tectonics is necessary for complex life. It's not. Some sort of tectonic activity is really important to sustain life on a body. However, plate tectonics specifically is not necessarily required for life. So yes, we should still look for life on bodies that maybe don't have plates. So anyway, we care. It is very important that we understand the tectonic evolution through Earth's history. However, not everyone agrees with this history that I've painted throughout this video and that Dr. Stern talks about in his paper. There are other hypotheses. Some, for example, argue that erosion, subduction, and metamorphism might have erased evidence of earlier plate tectonic activity, meaning that plate tectonics may have started earlier than we think based on the rock record, because maybe the record has been erased or altered in some way. Whereas others think that tectonic styles like lid and plate tectonics might overlap to a certain degree rather than switch entirely. So there's a lot of ongoing research in this realm of trying to understand tectonic evolution through Earth's history and our planet's tectonic future. If you want to learn more specifically within Dr. Stern's paper, I will link the full paper down below, as well as other references that are primarily by Dr. Stern and his lab group. And I want to hear what you think about how have tectonics evolved through Earth's time. Do you think plate tectonics' rarity or apparent rarity means anything for our search for alien life? Comment down below to let me know your thoughts and or any other papers that maybe I haven't seen on this that might also be interesting to cover on my channel. And with that, guys, thank you so much for watching, and I'll see you guys in my next one.